Good afternoon, everyone. I'm Ning, a PhD student of Huang University. I'm very honored to give this presentation here. The title of my presentation is a new type of hydrophilic QCM dew-point sensor. I will give the talk in 4 parts: background and motivations, sensor design and environment setup, results and discussion, and conclusion at last. Let's look at the background firstly. Dew-point is an expression of humidity. In meteorology, the temperature when the gaseous water in the air becomes saturated and condensed into liquid water and a fixed pressure. Figure in the right side shows the process of dew formation. When the ice was put into the glass, the temperature of the air in the glass decreased. The decreasing temperature makes the gaseous water put keep the state of gas and condensed into water drop on the glass wall. The temperature when the condensation occurs was the dew-point temperature. The value of the dew-point temperature was independent of the ambient temperature. For this reason, dew-point temperature has been internationally recognized as the most accurate expression of humidity measurement, and the actual moisture value transmission in the world was achieved through the dew-point temperature. Dew-point temperature also has important applications in meteorology, aerospace, medicine, scientific research, and industrial production. Therefore, the accurate measurement of dew-point temperature is very important. Till now, most of the dew-point measurement was through the conversion of relative humidity by using the mirror photoelectricity dew-point instruments. However, the conversion of relative humidity will introduce a certain measurement error, and the large volume and the high price of the mirror photoelectricity dew-point instruments restricted its application. And then more and more researchers turn to measure the dew-point by using the QCM technology. And we also have conducted a series of studies in this field. When the QCM was used for dew-point measurement, the particular cooled the QCM to dew-point temperature. In the process, the decreased temperature will introduce a frequency shift .ft, and the condensation will introduce a frequency shift .fm. Then we could get the frequency shift .f. So detecting the temperature when .f occurred, we could get the dew-point temperature. Our previous studies show that this method has advantages of high sensitivity and high accuracy. However, it has obvious backgrounds as the temperature frequency effect, and this method could hardly find an obvious agent value for dew-point recognition. For this reason, we proposed the hydrophilic QCM dew-point sensor. In sensor design, the graphene oxide was deposited on the electrode surface of the QCM through the electrode spraying system. The structure of the sensor was exhibited in Figure 2. In the sensor, the QCM was fixed by 2 copper pillars on the outer side. The graphite gas was used for the transmission of both heat and electricity. The thermal gas was used for the transition of heat only. And the particle and the heat sink was used to propose a better cooling condition. Figure 4 showed the characteristic of the material coating on QCM surface. The figure shows that the QCM coating with the film has a rougher surface which could absorb more water from the air, and it will benefit the sensor sensitivity. The experiments were conducted by using the measurement system. The pure nitrogen and the humidifier was used to generate gases with different dew-point. The MICHELL S4000 was used as a calibration device. The agent 4294A was used to drive and test the QCM. The temperature control and collection was realized by using a Liwei program compiled in the PC. The results of the sensor under different DuPont conditions was shown in Figure 6. In the figure, the dotted line and the solid line with the same color was the standard DuPont, which was acquired through the MICHELL S4000. The figure shows that with the decreasing of the temperature, the QCM frequency decreased and has a large frequency shift at the DuPont time compared with the initial frequency. However, there was no DuPont recognition characteristic at the DuPont position. Then a new method for DuPont recognition was needed. To recognize the accurate DuPont position, we fitted the original QCM frequency firstly by using the following fitting algorithm and calculated the first and second derivative of the frequency. The QCM frequency. The result shows that there is an extreme inflection point in the second derivative curves. We use this point as the point for DuPont recognition and get better measurement accuracy at less than 0.31 Celsius. To evaluate the performance of the sensor, the accuracy and the repeatability of the sensor was studied. The results show that the sensor could get better measurement accuracy at less than 0.31 Celsius in DuPont range 3 to 15 Celsius and better measurement repeatability for 3 days at less than 0.38 Celsius. Now I will make a summary of the studies. In the study, a hydrophilic QCM sensor combined with a smart algorithm was used for DuPont measurement. This method can obtain the unique characteristic parameter for DuPont recognition, and the influence of temperature on frequency in QCM cooling is eliminated. This is our content. Thank you for your attention. Thank you so much.